For decades, Pluto was basically a rumor, a faint dot at the edge of the solar system, barely changing no matter how powerful our telescopes became. Scientists thought they understood it well enough. Small, frozen, old, a leftover from planet formation that had been sitting there untouched for billions of years. Then on July 14th, 2015, NASA's New Horizons flew past Pluto at more than 30,000 miles per hour and sent back real images for the first time. Within hours, that neat picture started to collapse. Instead of a cracked, lifeless ice ball, Pluto looked complicated, young, active. It had smooth plains with almost no impact craters, which meant something had resurfaced them recently. It had mountains that rose higher than the Rockies, made not of rock, but of water ice. It even had a giant heart-shaped feature dominating one side of the planet, bright and geologically strange. This was not what anyone expected from a world so small and so far from the Sun. Pluto receives about 1,000th of the sunlight Earth does. Its surface temperature can drop below -370 degrees Fahrenheit. By every rule scientists had been using, it should have been frozen solid inside and out. No internal heat, no movement, no surprises. And yet, the data coming back from Pluto suggested something was still happening beneath the surface. Something was keeping parts of it alive in a way no one had predicted. Pluto wasn't just challenging what we knew about itself. It was quietly challenging what we thought small worlds were capable of. Before the flyby, Pluto looked like an easy case. It is tiny, about 2/3 the diameter of Earth's moon. It lives in the Kuiper Belt, far beyond Neptune, where sunlight is weak and temperatures barely rise above absolute zero. Worlds that small lose heat fast. Any energy left over from their formation should have leaked away billions of years ago. That mattered because geology needs energy. Mountains, cracks, glaciers, and resurfacing all depend on internal heat or tidal stretching. Pluto has neither. It has no large neighbour tugging on it. No thick atmosphere trapping warmth. No radioactive core big enough to stay hot for long. By standard planetary logic, it should have frozen solid early in solar system history. Scientists expected its surface to be ancient, covered in impact craters from billions of years of collisions, static, preserved like a fossil. There was another reason expectations were low. Pluto's orbit is extreme. It swings closer to the Sun than Neptune, then drifts far back out again. A single year on Pluto lasts 248 Earth years. That kind of orbit should make the surface hostile to long-term stability. Any atmosphere should freeze and fall to the ground for decades at a time. Any surface activity should shut down completely. So Pluto was filed into a mental category scientists knew well. Small, icy body. No engine. No story left to tell. That assumption shaped everything. Models, predictions, even the design priorities for the mission. The goal was to study composition and history, not ongoing activity. Which is why the first images were so unsettling. A world that should have been dead was clearly doing something. And once that door opened, scientists had to admit a deeper possibility. Maybe size and distance were not the final word on whether a world could still be alive. The most striking thing in the early images was impossible to miss. A bright, heart-shaped region spread across Pluto's surface, large enough to span the continental United States. Scientists later named it Tombor Regio, and it quickly became the key to understanding why Pluto looked so wrong. The left side of the heart, called Sputnik Planitia, was the real shock. It was incredibly smooth, almost no impact craters at all. In planetary science, that usually means one thing. The surface is young. Something erased the scars. Even stranger, the plane appeared to be made mostly of nitrogen ice. Not water ice, but nitrogen, the same gas that makes up most of Earth's atmosphere. At Pluto's temperatures, nitrogen behaves like a slow-moving glacier. It can flow, fracture, and resurface the landscape over time. High-resolution images revealed a pattern that looked like a patchwork of cells, each tens of miles across. The best explanation was convection. Warmer nitrogen ice, slowly rising from below, cooling at the surface, then sinking again. A cycle driven by heat coming from inside Pluto. That idea alone broke several assumptions. Nitrogen ice should not be mobile on a body this small unless there is an energy source keeping it active. Yet the evidence was right there, carved into the surface. The location of Sputnik Planitia raised even more questions. It sits almost exactly opposite Pluto's largest moon, Charon. That alignment hinted at a deeper interaction between Pluto's interior and its surface, possibly involving a subsurface ocean that helped reorient the entire dwarf planet. The heart was not just a surface marking, it was a sign that Pluto had an internal story scientists never saw coming. As the images sharpened, the heart was no longer the only problem. Pluto's surface was full of features that simply should not exist. Near the edge of Sputnik Planitia, towering mountains rose more than 2 miles high. On Earth, mountains like that form when rock is pushed upward by tectonic forces. On Pluto, these peaks were made of water ice. At Pluto's temperatures, water ice is as hard as rock. That meant these mountains were not piles of frost. They were structural, heavy, and old enough to stand without collapsing. But mountains alone were not the strangest part. Surrounding them were vast flows of nitrogen ice moving like glaciers. Some spilled out of valleys, others curved around obstacles. Their shapes showed direction and motion, as if Pluto's surface had been slowly reshaping itself long after its formation. Then there were features that looked like volcanoes, broad low domes with central depressions, possibly built from icy slush rather than molten rock. The leading candidates were Wright Mons and Pickard Mons, each stretching over 100 miles wide. If these were cryovolcanoes, it meant Pluto once pushed material up from deep inside, reshaping its surface from below. All of this raised an uncomfortable question. Where was the energy coming from? Pluto is too small for long-lived heat, at least by old assumptions. Yet its surface told a different story. One possibility was a subsurface ocean, insulated by layers of ice and kept warm by radioactive decay. Another involved the alignment between Sputnik Planitia and Pluto's moon, Charon, hinting that Pluto's interior might be denser and warmer than expected. Pluto was not frozen in time. It was slow, subtle, and cold, but it was still changing. Even if Pluto's surface had been surprising, its atmosphere was supposed to be simple, thin, temporary, barely worth measuring. Instead, New Horizons found something structured and dynamic. Pluto has a real atmosphere made mostly of nitrogen with traces of methane and carbon monoxide. It is incredibly thin compared to Earth's, but it is layered, active, and constantly changing. One of the biggest surprises came during the spacecraft's departure, when it watched the sun set behind Pluto. The light revealed dozens of blue haze layers stacked above the surface, stretching more than 100 miles high. These hazes are created when sunlight breaks apart methane molecules, triggering chemical reactions that form complex hydrocarbons. Those particles slowly drift downward, settling onto the surface and subtly changing its color over time. That means Pluto's atmosphere and surface are connected in an ongoing cycle, not isolated systems. Pluto's extreme seasons make this even stranger. As it moves along its elongated orbit, nitrogen ice sublimates into gas when Pluto warms, then freezes back onto the surface as snow when it cools. Entire sections of the atmosphere can collapse and reform over decades. Scientists once thought Pluto's weak gravity would let its atmosphere escape easily into space. New Horizons showed that loss is happening, but far more slowly than expected. Pluto is holding onto its gases much better than predicted. Taken together, the atmosphere told the same story as the surface. Pluto is not a static relic. It breathes, changes, and responds to sunlight in ways no one had anticipated for a world this small. Pluto was supposed to be the end of the story. A small, frozen body at the edge of the solar system, useful mostly as a time capsule from planet formation. What New Horizons found forced a rethink. This tiny world turned out to have weather, glaciers, mountains, and a surface that renews itself. It showed signs of internal heat long after it should have faded. It even hinted at a hidden ocean, quietly reshaping the dwarf planet from below. None of that fits the old rules. The real shock was not any single feature, it was the pattern. Again and again, Pluto behaved like a world that was still alive, just operating on colder temperatures and longer timescales. Slow-motion geology. subtle change instead of violent upheaval. That realization reaches far beyond Pluto. If a body this small and distant can stay active for billions of years, then many objects in the Kuiper Belt may be more complex than anyone imagined. Worlds once dismissed as inert debris could have their own internal dynamics, atmospheres, and histories still unfolding. Pluto did not lose importance when it lost its planet label. It gained it. By breaking expectations, it expanded the definition of what a planetary body can be.